Hello and welcome to Haemoglobin and the oxygen dissociation curves and this very long equation. It's important we know this and appreciate the names of these molecules, so I'm going to get into it. So HBs are like pretend chemical symbol for hemoglobin, and we know that it binds oxygen. So all these, this here, that is oxyhemoglobin. Oxyhemoglobin. So it's a word to use. You know it from GCSE. Use that word. However, it can be partially oxidized or fully, and therefore, yeah, over here I've got fully oxyhemoglobin. We need to know about how this like causes an S-shaped curve when I look at its dissociation that we're going to get to in a second. And really, it all boils down to the fact that this first bonding here is really hard. It's hard for that to happen. Okay, hemoglobin needs to be like in like a high oxygen environment for it to bind oxygen in the first place. As soon as it binds one, it binds it easier. So this is so this is easier. I'm not sure what's going on there. Nope, can't spell easier. Easier. This is easier. Oh, like a double E. Easier, and this is easier. So it gets easier and easier and easier to bind oxygen the more oxygen it binds, because when hemoglobin binds oxygen, it changes its structure. So we're just going to give a few facts about hemoglobin first of all. So first of all, it's a protein with it's got quaternary structure, fourth degree structure. It's made of 4 polypeptides, each with a heme group. And that's made of an iron. Iron, ion. As in each polypeptide has an iron ion, and that binds it. Yeah, and when it binds oxygen, binds O2, it changes shape. That makes it easier. Now, I keep putting easier here. When I say easier, we change its affinity for oxygen. I'll finish this sentence first. That makes it easier to bind subsequent oxygens up to its maximum of 8 or four oxygen molecules. Because oxygen goes round in its pairs, doesn't it? So making it easier, we we can say that it's got a higher affinity. Affinity is a liking for. I've got a very high affinity for salt and vinegar crisps. I've got a very low affinity for raisins, currants, and sultanas. Is there anything else I want to say here? Don't think so. I'm going to get to these blob diagrams once we have a look at the graph. Okay, so because of how it binds oxygen, it gives us an S-shaped curve. Now my curve doesn't look very S-shaped, however it is, yeah, because it is curvy up at the bottom, and then it's curvy over at the top. It's an S-shaped curve. I could show it better, but I want it quite high here for what I'm showing. There was one other factor I needed to get through as well. Hemoglobin is found in red blood cells. There are millions and millions, like 200 million molecules of hemoglobin per red blood cell. Okay, so it's not as if a red blood cell is a hemoglobin. Okay, we get a lot of that in written answers, as though a red blood cell has high affinity for oxygen. Yeah, a red blood cell is just a container with loads and loads of hemoglobin in it. And when I say loads of loads, 200 million molecules of hemoglobin in that tiny red blood cell. And therefore, we can study how hemoglobin carries oxygen by doing a graph like this. So I've got my partial pressure of oxygen in the environment. Pressure is measured in pascals. It's such an insignificant number that we normally measure it in kilopascals. Okay, it's kind of the same as percentage, but we can't have percentage because, if I go up a mountain, there's less oxygen in the atmosphere, but the percentage of oxygen stays the same. But if I go up a mountain, the partial pressure of oxygen reduces, as in the pressure due to oxygen, because there's less air pressure. So, but you can think of it like amount of oxygen. Um, and there's like two figures to kind of think of that when it's about 12 kPa, that's like the O2 in the alveoli. Alveoli. Yeah, so that's like in the lungs. When it's down at 2, this is like a respiring muscle, a muscle that's working. Yeah, so it drops massively. So when hemoglobin, or sorry, when red blood cells pass through the lungs in the capillaries and the oxygen diffuses into it, it's going to get to here. And if I kind of go across, I've kind of missed the 100 mark a bit, but it's going to get roughly 100% saturated, like 99.8% saturated. And per red blood cell, it can be 99.8 because there could be a few molecules of hemoglobin deep inside it that have only bound 3 oxygens and not 4. Okay, but it's going to be roughly fully saturated. When that same red blood cell gets to a respiring muscle, so the zone around this respiring muscle is very low in oxygen, it's down at 2 kilopascals, then the hemoglobin is only, again, let's call this 25% saturated. Okay, so in effect, when a red blood cell gets to respiring muscles, it gives up 3/4 of its carried oxygen, and it carries on past, carrying a molecule of oxygen that the muscle desperately needs, but we're too stupid to give up that final oxygen, and that just doesn't make sense, does it? For a red blood cell to go past a muscle with carrying oxygen with it away from a muscle that desperately needs it, and that muscle might be the one that's powering my legs as I run away from a saber-toothed tiger that's about to eat me or something in my evolutionary past. Yeah, so again, we need a mechanism to change that. So we have a way of shifting this curve, yeah, to the right. So when I shift this curve, I'm still going to start at 0, but I'm going to kind of come up here. I'm going to do that. So this is our curve that shifts to the right. It's called the Bohr shift. And all it means now is that the vast majority, this is now down at, let's say, this is now 5%. So 95% of the oxygen is now going to be released to the respiring muscle tissue rather than just 75%. So it's a significant gain over the other one. Okay, and we're going to look at what happens when a curve shifts to the right. Bohr shifts on the syllabus. However, there can be other animals that have compared to human. So this pinky purple line could be human hemoglobin. Well, it might be that there's a pigeon that's got a curve that's to the right of the human curve. It doesn't shift to the right; it just is to the right. So we're gonna look at what we say when it shifts to the right, and then we're gonna also say what happens when it shifts the other way, when it shifts to the left. Yeah, so that's when it kind of looks like this. Yeah, so this is our left shift. This is like the classic is like fetal hemoglobin. Again, it's not shifting. There, it's just on the graph it has shifted, but a fetus has got a different kind of hemoglobin compared to an adult. And your class as adult when you're like in terms of hemoglobin, when you are born, you transition from fetal into adult hemoglobin. So by the age of 1, you will have adult hemoglobin, and you'll have like a mixture for a while whilst you're younger. I don't know the exact numbers. Let's have a look at this shifting left and right, because you can understand this, or you can just like learn what do you say if it's to the left or to the right. Okay, so left. This is our fetus. Fetus down here. I refuse to give up my O in fetus. It's the British spelling, American spelling, fetus, but I'm holding out on fetus. And shift to the right is going to be our Bohr shift. But I'm going to pop another examples, a few examples down after. So it says the effect on hemoglobin's affinity for oxygen. Well, if I shift to the left, it's got greater affinity. Greater. Yeah, it's got greater affinity. It likes oxygen more. So if I just go back to the graph, if we take a partial pressure, let's go up from, find a pen that you can see, got a green here. Let's go up from about 6. I've got 6 kPa. Let's go up to the line at pink. It's at, we're going to go across, all right, it's at 90% saturated, but my blue line's at 100% saturated. I'm slightly off on that 100. But yeah, so if fetal hemoglobin is 100% saturated and adult hemoglobin is only 90% saturated, it likes oxygen more. Yeah, it can bind more oxygen. Yeah, so the ability for hemoglobin to become fully saturated, this is also higher. Yeah, so it gets fully saturated at lower partial pressures. So let's just put that into answer. So it's higher. Yeah, so it becomes fully saturated at lower partial pressures. Obviously, I'm not writing SAT full stop and PPs in an exam. And then this is the important one. What's the benefit to the organism of being able to bind oxygen better than another kind of hemoglobin? Well, you can scavenge oxygen from the other hemoglobin if you're a fetus. If you're like a lugworm or something, you can scavenge oxygen from a lower oxygen environment. Yeah, so it's an ability to bind oxygen in lower partial pressure environments. And if you can do that, you can obtain oxygen. For what process? Oh yeah, I know, aerobic respiration. And as you know now, it's the terminal electron acceptor. In aerobic respiration, it binds the proton and the electron and changes into water, allowing all the other reactions within the mitochondria to take place. Bit of bonus teaching there. I'd have that on a t-shirt. Oxygen is the terminal electron acceptor. You go into an exam with your mantra of what oxygen's role is. Anyway, and if you do aerobic respiration, you can gain more ATP. You can gain more ATP per glucose. Like 38 ATP. Because the alternative is to do anaerobic respiration and make 2 ATP. Yeah, so that's like really a bad strategy for an organism. So I've got all this trouble of getting some food. I managed to eat some food. I've got to digest it into glucose, and then I'm going to get 2 ATP from it because I've got no oxygen. Ludicrous. Okay, so yeah, so you can get oxygen, and therefore you can make loads of ATP. The downside of this is that the hemoglobin's also not that good at giving it up. It's better at binding it, but it holds on to it. So if we go back to our respiring muscle cell here, it's only going to give up it's, what's that number there? Let's say it's 40%. Oops, come off there. So 40. So it's only going to give up 60%. Now, does that matter to a fetus that it's not going to be able to use its muscles massively? Again, no, it doesn't, because it's inside its mother's uterus. It's just like doing the occasional kick and punch, which, I think pregnant women celebrate. Oh, look, it's moving inside me. So it's not having to run away from a predator. So it is no big drama. It is a penalty worth paying. Same for a lugworm. A lugworm's just under the sand, filter feeding. It doesn't matter if it can only do a little bit of aerobic respiration. Crucially, it's doing it super efficiently and getting 38 ATP. Okay, so if you have a curve to the left, you tend to be a slower organism. So yeah, so this is like slow organisms, e.g. worms. Yeah, things that live in almost anaerobic environments. The only other example that comes up possibly is also myoglobin, that's got a super high affinity for oxygen, and it's like an emergency store of oxygen. It will only release its oxygen in absolute dire circumstances. And when you do about muscles on the side of the course that I don't teach, on the 3 side a week, then you will learn about myoglobin then, and its role, that it's found in a certain kind of muscle cell that is designed to kind of like, well, they are muscle cells that are red in colour, and therefore they are really good at like staying aerobic. So let's do the other one. So yeah, we're going to do the shift to the right. So this has now got less affinity, which sounds crazy, doesn't it? It's got less affinity. Ability for hemoglobin to become fully saturated is less. So it's like, well, what's the benefit? And it's kind of less in inverted commas, because things like birds have got more efficient lungs and therefore can get it fully saturated. I mean, on my diagram, I've kind of like shown it like still practically getting there. So you can see my red line here; it's slightly below my purple line. Um, if it was a bird like a pigeon hemoglobin like looks like that. However, they've also got more efficient lungs because they don't have any residual volume. So yeah, so this is like bird lung over here, so it does get fully saturated. But yeah, it's not good um, at binding more. So I would never talk about that. I would talk about what's the advantage to the organism of this. Just bathing the cat here. Hang on a second. Right, I'm back. The cat one. So I'm doing this with cat now. Right. So yeah, benefits to the organism. Well, the benefits are, again, let's go back to our red line again. So we're on this bore shift, and it's down here. Yeah, that it means that hemoglobin has less affinity, therefore it gives up more of its carried oxygen. So it's still getting like pretty much fully saturated. Yeah, but it is giving up more. So yeah, ignore the ability to become fully saturated. Yeah, but like ignore. Um, yeah, the benefit to organ is that more of the O2 carried is released to respiring tissue. So there's more aerobic respiration, therefore more energy. Well, more ATP for muscle contraction. Yeah, I can say that it avoids anaerobic conditions, and therefore lactic acid formation, therefore muscle fatigue. Yeah, so it's weird how it's the same benefit. Yeah, so if it shifts to the left, you've got more oxygen for aerobic respiration. If it shifts to the right, yeah, you've got more oxygen for respiration. However, this is releasing lots of oxygen, and therefore it's a faster release of oxygen. These are fast organisms that have it this way. So yeah, so bore shift is one example. But things like the um, pigeon will be an example. You can't afford to get cramp if you're flying. Yeah, because if you get cramp and you get muscle fatigue and cramp, then you're going to spiral down to earth and die. So yeah, it avoids anaerobic conditions. It's got super emerging lungs, and therefore it can ensure that its conditions are aerobic, and therefore it doesn't make lactic acid in the first place, and therefore it's got powerful flight all the time. So so in a question, just in summary, because I've hit the 20 minutes mark. If it comment on the affinity for oxygen, is it higher or lower? And I just need to show this quickly, don't I? Sorry, because I said I'd talk about these. This is hemoglobin, and left and right. When it's got higher affinity for oxygen, it means that it's got these bonds. I'm kind of showing it. So this is the first oxygen it binds. Okay. This is the second oxygen it binds. This is the third oxygen it binds, and then that's the fourth oxygen it binds. So the fourth oxygen's bonded really lightly. There's only a very thin bond. Then that one's bonded a bit more tighter and tight still. And when we shift to the left, these bonds are quite high. When I shift to the right, well, my weak bond is now really weak. It's barely held, and this one's kind of just held, and that one's a little bit more firmly held, and this one over here, again, I don't want to give an impression that it's even similar, is even less. So it's kind of like it's barely holding on to the oxygen on this side. It's desperate to let go of it, and as soon as it hits a low partial pressure zone around our body, then it will dump the vast majority of the oxygen, whereas this one is designed for holding on to oxygen. But again, it doesn't matter to the organism because they are not worried about being that active. So hopefully that was useful. Again, you can just learn whatever question context they have. It will always be, is it to the left or the right of the of another curve, or compare these two organisms, one's to the left and one's to the right of the other. Again, it's still exactly the same thing. Okay, hopefully that was useful. Take care.